When freezing rain hits an electrical grid, the sheer weight of the ice buildup can snap power lines and crush steel transformers. During the Great Ice Storm of 1998, this exact vulnerability brought the northern United States and southern Canada to a complete standstill, leaving millions in the cold and dark for weeks. Right now, our main defense against freezing weather involves brute force. We expend massive amounts of electrical heat to keep machinery running, or we spray millions of gallons of toxic chemical fluids to melt the ice off airplane wings. Ice buildup is a relentless physical problem, one that traditional human engineering has struggled to solve without heavy economic and environmental costs. But down in the Antarctic, the environment is vastly more hostile than any winter storm. Gentoo and Humboldt penguins spend their entire lives plunging into sub-zero oceans and stepping right back out into freezing air, yet they never ice over. A common assumption is that these birds relied on a chemical coating to repel water and ice, specifically a waxy substance secreted from their preen gland. That preen oil actually acts more like a feather conditioner. It keeps the biological structures supple and flexible over a long winter, but it isn't the primary reason they stay dry. A penguin's survival depends on its physical architecture, a set of specific mechanical solutions that keep ice from ever taking hold. Comparing a penguin feather to a flying bird, the first difference is the central shaft, or rachis. A penguin's rachis is uniquely broad and flat, accounting for up to 70% of its mass. This allows the feathers to overlap, forming a dense physical shield. Branching off that central shaft are smaller structures called barbs and barbules. These tiny fibers zip together to create a biological mesh. The microscopic gaps in this structure are too small for the surface tension of water to penetrate. This outer shield perfectly blocks ocean water, but keeping dry is only half the battle. Surviving extreme cold requires an entirely different defense mechanism underneath. Closer to the skin is the downy afterfeather. Microscopically, it's covered in tiny 30-micrometer extensions called cilia. These hook together using a stick-slip action, sliding easily in one direction but locking in the other. This creates uniform air pockets that act as radiation shields, reflecting heat back toward the bird. Even with heat trapped and water blocked, extreme sub-zero temperatures should still freeze any surface moisture directly to the bird. To stop ice adhesion, the feather's nanoscale surface features tiny pores that counterintuitively draw in water. When temperatures drop, this trapped water is the last to freeze. As it expands, the physical force fractures the larger ice sheet above from the inside, causing it to slide off. The feather actively uses the natural expansion of freezing water to destroy ice buildup from the inside out. Material scientists in a field called biomimetics are now extracting these biological defense strategies and testing them in industrial applications. Researchers at Beihang University are weaving polyimide nanofibers to mimic the feather's insulation for electrical cables, while a team at McGill University has developed a laser-machined woven wire mesh that copies the penguin's ice cracking surface. This chart compares ice accumulation on standard stainless steel to the new biomimetic mesh. In wind tunnel tests, the laser-machined mesh was 95% more effective at resisting ice. Unlike current protections, these surfaces need no external energy or toxic chemicals. By reverse engineering the penguin, we are finding ways to translate biological defenses into materials that could protect our infrastructure on their own terms.